Great, thanks everyone. First, I want to share a little about myself. I recently left the academic world of being a biologist and joined the business world as a developer. So this started last fall. Before that, I was a graduate student in San Francisco at UC San Francisco, and then I moved to Israel about 5 years ago to do a postdoc, and then joined AppsFlyer last fall as the first member of our data team. I could say now that we're actually going to be 6 members in a few weeks, so we've grown pretty fast. I'm going to tell you about our real-time attribution architecture to give you an overview of the business that we're in. And then I'm going to dive deep into one of the reports that we generate for our clients and use that as a way to show you the evolution that our data system has taken. And then I'll share just some troubles that we've had using Spark and how we've solved them. And hopefully that will be beneficial for all other people. Our business is mobile attribution and analytics. The first part is attribution. And what that means is when a user clicks on an advertisement on their cell phone, the app owner would like to know which ad is responsible for the install, and so we provide that information. Mechanically, the way it's done is after the click, the click redirects through our server generally before it goes on to the App Store. And then once the app is installed on the machine, then on the first launch, we get a message directly from the phone, and then we can make the attribution based on that message. We do all of this, we do the attribution in real time, and that's to support a fairly specific use case called get conversion data. So if you clicked on an advertisement for hotels in New York, and then you didn't happen to have the application installed, you would go to the store, you would install the app, and then when the app first launches, the app owner would like to show you a page about hotels from New York. So we allow them to do that because while the app is first launching, they can ask us a few hundred milliseconds after the first launch, they can ask us which ad is responsible for the install. This is our real-time architecture that allows us to do the very fast matching. We have 2 large messaging queues. The bulk of our data goes on to Kafka, but for faster performance and latency, we use RabbitMQ. So for the actual matching, those events go into RabbitMQ and are quickly processed so that we can get the data back to the client. And then other events, including every subsequent launch of that cell phone app and any in-app events that the app owner has programmed using our SDK, which they embed, all those events go into our main Kafka pipeline. We're doing this at a pretty large scale. Currently, last time I checked, we're getting about 7 billion events a day from the cell phones. And each one of those is a pretty meaty JSON document. So talking about a fair amount of data that we have to work through. Once the events are in Kafka, then we have small services arrayed around the Kafka queue that can drive the dashboard, that can send in real time the installs back to the app owner. And Then at the end of the Kafka queue, we use a service called Secor from Pinterest. And that service makes safe dumps of your Kafka queue onto S3. And so that allows us to persist our data from Kafka onto S3 for future storage. And so after that is done, that's where my job really begins, is doing batch processing using Spark on the data that we persisted off our Kafka queue. This is the retention analysis that we do for the clients. It's fairly straightforward. We are asking a question. All the installs that a client got on a particular day, how many of those do we see launch the app again on subsequent days? And so what makes this a bit challenging, though, is that the scale is pretty large. For each install day, we have about 30 million installs. And then we have to link those up to over 5 billion sessions. A session is a launch of the cell phone app. So that's where the challenge is for us. Also, we want to produce these types of comparisons across many dimensional splits. So I don't think you can read this, but it says we want to split by the campaign that the ad was in, or the media source that the ad came from, and the geo where the app was first launched, whether it was launched on Wi-Fi, that kind of stuff. And dimensions are expensive because every time you split your data, you get more rows in the output. The first iteration of this actually didn't involve Spark. It only supported 2 dimensions, only really 1 dimension. It was written using a really interesting library called Casco Log, which allows you to do logic programming that gets translated down into Hadoop MapReduce. And the library is also written in Clojure, which is our main programming language at AppsFlyer. So this was a fun choice. But as our scale has gone up, eventually this process just one day stopped working. And I was tasked with trying to figure out what went wrong, and dug around a little, and it had run out of memory. So I don't know, added some more instances, made the memory a little bigger, and it ran for a couple more weeks, and then it stopped again. So we decided rather than keep pushing on this, it's time to develop a real product that's got a lot of dimensions and a lot more powerful for our clients. So we decided to re-implement the retention analysis, and this time use Spark SQL. The data coming off of the Secor project is in Hadoop sequence files, where the key of the file is just the offset number from Kafka, and then the value is just the raw JSON that's in there. That's nice because we have like a very safe representation of our data that's never going to change, but it's not so great for querying and doing any kind of analysis on, because every time you do something, you got to bring it up, maybe parse it with a schema, and so what we did was we created a process to convert those into Parquet files and bring the data up into Spark, and then pick just a few of the columns that we're going to need for the retention analysis, and then write them back down into Parquet files, and then run over those Parquet files essentially using Spark SQL, because now we have a table for the installs and a table for the sessions. So it's basically just a select and a join to get our retention analysis. Let's see. This is just talking about an optimization that we did to the original data. So the first form of the data just has the cohort day, which is another word for the install day, and then the day that the particular launch happened, and then for those particular dimensions, how many users were seen. And to make the data easier to query from the front end, we then pivot that out and get all the day values together. But even after pivoting it out and aggregating it again, we still have about 1 billion rows of data. So currently, we're putting this data into Redshift, but we're not super happy with that. Redshift isn't a great database for user-facing queries. So we're moving to a new database, a Druid database that I'll talk about in a second, and we'll probably be putting it there. There was another problem with what I just described, which is that we read the data up, and we only picked a couple of columns, and we applied some business logic to those columns, and then we wrote that out as Parquet. But what if the business logic evolves, or we need a new column that we didn't think we needed? Well, then we're in trouble. So now we're doing something that we call schema on read. So we have first a process that converts the JSON almost completely without any change of schema into Parquet. And then we create a shared library that's written in Spark SQL that allows us to access that raw data with all the business logic applied. So far, that seems to be going really well. And one advantage of that is that we can now use that same shared library. Here, it's the SQL in the middle there. And we can do both streaming and batch operations on the same data using the same business logic. We don't have to duplicate that business logic in any way. So here, what we're starting to do is use a database called Druid, which is a really exciting project that we've started using, and we're super happy with it. You can stream data into it, and it has a Lambda architecture inside that you don't have to mess with. It rolls up your data according to the configuration that you choose and passes it on to historical storage. And then you can query it both both for the new data and the old data. The other advantage is you can also feed it data from a batch process, and it'll automatically rewrite all the historical data. So if you want to evolve your scheme over time, you just run a new process, put all new data in, and it goes in really fast. They use a very advanced indexing. So they create a full inverted index for every column of your database. And so that allows you to query by every arbitrary combination of your data. And they use some smart compression and index operations to make those queries very fast and to make the data very compact. So far looks like a great project for us. And this is going to allow us to serve our clients a really fast view of the dashboard that has a lot of granularity in terms of dimensions. We couldn't find any other product that can do that. This is open source product, by the way. So now I'm going to talk a little bit about how we got into using Mesos as our cluster manager. So we don't use HDFS, so that made Yarn a less obvious choice for us. Also, Spark and Mesos have a long history. Both came out of the AMP labs. So we started using the EC2 scripts that Nick just told us about. They were slow, and at the time, about a year ago, they didn't support the VPC functionality in AWS. If you don't know what that is, it doesn't matter, but we needed to be in there, and Mesos is super easy to set up as well. So I was even able to help with the DevOps side of things. So. You get a very nice UI from Mesos. You can find your jobs, all the logs. This is less of an issue now that the Databricks platform is here, which also has a very nice UI, but at the time, this is pretty handy. Mesos is, the Mesos masters are really fault tolerant. You can kill one of them and they fail over and your jobs keep running. We tried it out, it actually works. Also, you just, the nodes register themselves with zookeepers. So if you want to add more nodes to your cluster, you just launch more nodes. They add themselves in. You want to reduce the size of your cluster, you just kill some nodes and they leave, no problem. We're currently using Chronos as the job scheduler, which we're less happy with. You can read this blog from Afir and the Jepsen project, if you're familiar with that. It didn't do so well when he stress tested it. We're probably going to look into Aurora long term, but I can't tell you how that's going yet. So now I'm going to go through a few of the specific problems and challenges that we dealt with over the past year. So like I said, we're not using HDFS, and this is great for a lot of reasons, but it's challenging because S3 storage is not the same as HDFS. So we started off using the S3N connector library. It generates lots of timeout errors, and for some days, it'll just stop running at 5 p.m. every day. All your jobs will die. I don't know why. I think it gives a DNS error. I think Amazon did some kind of DNS swap at 5 p.m. every day, and that knocked us off. At the time, we were using max failures per task, up to 20 max failures, and that would allow us to get some work done, but it wasn't ideal. We switched to S3A, and things have been great ever since. Just be careful, you can't use the version of S3A that's in Hadoop 2.6, because it'll generate 1 million partitions for your data. So. You also, if you're going to use S3, you have to use a direct output committer. These can be found online, or there's one built in for the Parquet files. And they work great. The issue here is that a renaming of files is an expensive operation in S3, whereas on HDFS, it's like a file system, so it's very fast. The normal way that Spark writes its files out, it writes a temporary directory full of files and then renames them all. That can take 10 or 20 minutes if you have like 1,000 or 10,000 partitions. So it's not perfect, though. You can't use speculative execution with this because they'll try to overwrite their files. We have still some poor recovery. If we have a failure of a task during the write phase, we get poor recovery. And I think that's because we're using the direct committer, the direct output committer. Personally, I've stopped using the .0 releases. But actually, the 1.6 release looks really good so far. But we got bit really hard by a bug in 1.4 that, combined with the direct output committer, would lose up to 5% of your data because it had a bug in the way it was naming the output files. There's two modes for running Spark on Mesos. There's the Coarse-grained mode and the Fine-grained mode. In the past, I might have gone over the Fine-grained mode a little more, but essentially it's going to be removed from Spark 2.0, and it should be considered deprecated. So you can't really use it, but the upshot is that the Coarse-grained mode is all you have, and it's pretty good. It's very stable, but it has a couple of disadvantages. So the way the Coarse-grained mode works is your Spark driver asks the cluster manager for some resources. It gets some machines, and it takes them over for the entire job. Now, if someone else wants to launch a job, they're out of luck. If you took the whole cluster, they have to wait. This can be, so you can, there's two solutions. One, you can launch your job and say, OK, I don't want to take the whole cluster. I'll take half of it. But this isn't ideal either, right? If you're only using half the cluster and then nobody else launches a job the whole time you're running, you could have gotten your answer twice as fast. So it would be great to get some real preemptive scheduling. I'll talk about that in a sec. There is a solution for one of the problems, which is as you get to the end of a stage, maybe you're holding on to 500 cores in the cluster, but you're only using 50 of them because you're just waiting for the last tasks in that stage to finish. So there's a feature called dynamic allocation that you can enable, and it'll kill off the executors that you're not using. Unfortunately, in our experience, that feature is only working well with the smaller jobs that we run. The big jobs are consistently failing there, so we're going to have to keep trying it and try to figure out what's going wrong there. If you're launching your own clusters, use as big a machine as possible. I think this makes some intuitive sense because you're minimizing the shuffle if you have 4 machines that are very large versus 20 machines that are very small. And if you want to tune if you're running out of memory and you want to give more memory to each task, kind of paradoxically, the setting that you need to use is the Spark task CPU setting. And the way to see this is that in coarse-grained mode, each executor has a whole machine. And so if you tell it, in our case, we use machines that are big, so they have 32 CPUs. So if you say, I want each task to get 32 CPUs, then you'll get all 200 gigs of RAM off that machine for the tasks. So that's why this setting is actually a RAM setting for us. I'm going to skip that, and I want to get to one thing that just happened last week. We were experimenting with this new Druid database. It wasn't yet in production, luckily. And I noticed like some days had twice as much data in them than other days. And I couldn't figure out why. And it turned out what we had been doing is we've been consistently getting a random error in our Spark job. So we were capturing that exception in the driver and then respawning that Spark job. And that sounds like it would work well because we respawn the job in overwrite mode. So it should go to the directory where it wants to write the files out, delete anything that's there, and start writing again. But S3 is eventually consistent. So in the time since we first, we launched the new job, there's still files in the interwebs making their way in AWS to get into our folder. And so then by the time the job finishes, you have 2 copies of the data sitting there. So that's part of the excitement of using an eventually consistent data store. But always remember, S3 is not HDFS. And that's all. If any of you are looking for a job in Israel, then come and see us. We're hiring. And thank you so much for coming.
So we're using Mesos in Finegrained Mode.
Oh, okay.
And the main reason for that was, so we have like multiple users that want to use the entire cluster.
Yeah.
And if you use coarse grained, even with dynamic allocation, like a long-running task will just consume long-running job will consume the whole cluster.
If you have one long-running map job, you'll take the,
Yeah. So do you have any tips, or have you had this similar issue?
Yeah, we have the same issue. We're not sure. Maybe I'll use your question to show a slide that I skipped, which is Mesos is adding some new features that I hope the Spark framework will start to take advantage of. They have a new concept of an inverse offer.
Yes.
So normally when the driver asks for resources from Mesos, it receives an offer of resources from Mesos. And this is a way that Mesos can offer to take instances away from you. And so that would allow true preemptive scheduling.
Exactly.
So I hope that comes in. I would.
Thanks.
Yeah.
I actually work for TypeSafe, which is contributing to the integration of Spark and Mesos, and with Mesosphere, actually, not to take total credit. We are actually working on the inverse offers. And the other thing that is coming pretty soon, certainly by 2.0, is breaking this requirement that there can only be one executor in coarse grain mode per node. So it would just be one executor per N tasks instead of one task like you have in fine-grained mode. So I think eventually all of the advantages of fine-grained mode will go away, but it might be a little painful for a short period.
Yeah. I didn't mention it, but the fine-grained mode was incredibly unstable in our hands, so there was not really any advantage.
It's also like there's two implementations in Spark for coarse grain, which is really bad, actually.
But I'd also like to talk to you afterwards, just to
sure.
make contact.
While you're answering questions, do you know about oversubscription in Mesos as well in Spark? It's kind of like reverse offers, I guess, but not really. Yeah, just wondering, since you happen to know, if they're working on oversubscription basically in Mesos. I had just a small question about with Spark and Mesos specifically, how you're tackling accessing the UI, the Spark UI because you're using Kronos, which also makes it even harder. So if you want to actually access the Spark UI in a dynamic environment, like how are you getting to it?
Okay. Currently, I got the DevOps guys to do just a little bit of stuff in console so that they do a little bit of service discovery in console and give us a CNAME that always points to the master. And I'm sure I could share what they're doing. It's nothing sophisticated.
We do a similar thing. So.
Yeah.
Any other questions? Okay, great. Oh.
So are you using client mode or cluster mode for?
I get confused about which one is which.
The driver, is the driver?
The driver's in the cluster,
Okay.
Yeah, not on the... have you experimented with the client mode?
So we're actually just using client mode because it's easier to debug and get the UI of the Spark UI.
Yeah. Okay, we find finding the UI super easy. So, and now in 1.6, the Mesos UI actually has a real link, a hard link to the Spark UI.
Yes.
So it's super easy to find the UI.
If there are no more questions, I think we're done with this segment. So yeah, just another round of applause.
Thank you.